In this video, we introduce the concept of selective precipitation. Right, let's suppose that we have a mixture of two ions, calcium and barium ions, in a solution. Alright, so there is our experimental device, and you have calcium 2+, and then you have barium 2+. The concentrations of each are going to be calcium 2+ is going to be in a molar concentration of 0.10 molar, and then barium 2+ is going to be in a concentration of 0.20 molar. Right, so the idea is to try to separate these two ions by selective precipitation. Here's the story. We want to add a counterion that forms an insoluble salt with each one of them. But if we choose that counterion wisely, we may be able to come up with two insoluble salts with very different solubility products, and that might give us an opportunity to precipitate selectively one of them, the one with the lower solubility product, before any amount of the more soluble salt precipitates. Alright, so let's try to see if we can go through a numerical problem and explain that slowly. What we're going to do is add here sodium fluoride. It's a salt, right? And then when you put it in a solution, you will have sodium plus ions and fluoride minus ions. Right, so there's going to be reactions that form between calcium and fluoride and barium and fluoride. Those will be precipitation reactions because calcium fluoride and barium fluoride are insoluble salts. Okay, so let's write each one in turn. The barium reaction will be barium 2+ reacting with 2 fluoride minus. That generates calcium fluoride, which is an insoluble salt. Sorry, barium fluoride, which is an insoluble salt. Okay, and the solubility product for this barium fluoride has a value of 2.4 10 to the minus 5. Okay, then we have that calcium will also precipitate 2+ plus 2 fluoride to generate calcium fluoride. It's a solid, and the solubility product of this salt is 4.0 10 to the minus 11. Alright, so here's kind of the important aspect of this problem. Notice that the solubility products of both salts are very different, right? That of calcium fluoride is much molar than that of barium fluoride. So the idea here is that if you're very careful in the addition of fluoride ions, right, because it's much easier, because this salt is more insoluble, you can try to precipitate that first before any of the barium fluoride precipitates. Okay, so we're going to try to see how this works by asking the following questions. First, what is the concentration of fluoride minus at which you start to see precipitation of calcium fluoride? Then what is the concentration of fluoride minus before you start to see precipitation of the barium fluoride? And then, because calcium will precipitate first, how much calcium is left over before barium starts precipitating? Alright, so let's try to see if we can try to do each one of those problems in turn. Alright, so the first question is, well, how much fluoride do you need to see any calcium precipitation? Well, you can do that from the solubility product. Notice that the solubility product is going to be equal to calcium, that's fluoride, squared, right? And then you know this number. This is just the concentration of calcium that you have initially, 0.10 molar. And then you know the solubility product as well, which is 4.0 10 to the minus 11. Right, so you can conveniently here solve for the concentration of fluoride minus, at which you will start to see precipitation of calcium fluoride. And then you will find that this is equal to the solubility product over the concentration of calcium 2+, which is the same thing as the square root of 4.0 10 to the minus 11 over 0.10 molar, right? And that gives you concentration for fluoride minus for calcium fluoride precipitation of 2.0 10 to the minus 5. Right, so here you're going to be adding solid sodium fluoride, and the moment that you get a concentration of sodium fluoride or fluoride ions larger than 2.0 10 to the minus 5, you will start to see calcium fluoride precipitation. Okay, let's try to do the same thing now for barium fluoride. Right, so for barium fluoride, you would do exactly the same thing. You would say the solubility product of barium fluoride is just the concentration of barium ions multiplied by the concentration of fluoride ions squared. And then you can solve for the concentration of fluoride ions as the square root of the solubility product for barium fluoride divided over the molar concentration of barium. And let me write here what those numbers are. 2.4, 10 to the minus 5, divided over 0.2. And this gives you a value of 1.1, 10 to the minus 2 molar. Okay, so here's again a demonstration of selective precipitation. All right, you can add fluoride ions, right? And initially the concentration will be very low if you add very low, but eventually that concentration of fluoride will go over 2.0 10 to the minus 5. At that point, you start to see precipitation of calcium fluoride. However, that amount of fluoride is not enough to actually get over the solubility product of barium fluoride, and then barium fluoride will not precipitate, right? So again, for concentrations of fluoride that are larger than 2.0 10 to the minus 5, but lower than 1.1 10 to the minus 2, then you will only observe precipitation of calcium fluoride. Okay, so as you add that fluoride, the calcium will continue to precipitate, and that means that calcium starts to be removed from solution. Eventually, you add enough fluoride that you get to this point, and at that point, then you will start to see as well the precipitation of barium fluoride. Okay, but if you stop right at that point, you can clearly separate the calcium fluoride and then from the barium fluoride. Right? To see how good the separation is, what we're actually going to calculate now is, well, suppose that we add fluoride up to this point, but just a little bit. At that point, we'll only have calcium fluoride precipitated, and then all of the barium will still be in solution. The question is, well, is there any calcium left in solution that has not precipitated, and how large that amount of calcium that is left in solution, how large is that? Okay, so here's the idea. What we're then going to do is take the limiting concentration of fluoride that you can add before barium precipitates, and then see how much calcium is left over with this limiting concentration of fluoride at which barium fluoride starts precipitating. Right, so here we go back to the solubility product, and then what we actually do is just simply calculate what is the concentration of calcium left over. Okay. So we will have here the solubility product is going to be equal to the concentration of calcium 2 plus times the concentration of fluoride minus squared. But again, what we do now is just plug in here the limiting concentration of fluoride at which barium starts to precipitate here, and that would be 1.1 10 to the minus 2 squared, and then replace this by the solubility product of calcium fluoride 4.0 10 to the minus 11, and that will give you the amount of calcium left in solution. And of course, this amount is going to be very, very small. Calcium 2 plus is equal to 3.3 10 to the minus 7 molar. Okay, we can carry one more calculation that is going to let us know what is the percent of calcium left in solution compared to the initial amount. And this is a straightforward calculation. This is the percent of calcium left over. That is simply the concentration of calcium 2 plus at equilibrium before barium starts to precipitate, and then over the initial concentration of calcium 2 plus. All right, so we have this is a percentage of times 100%. Okay, so this is going to be equal to your concentration of calcium 2 plus at the point where barium fluoride starts to precipitate, so that is 3.3 10 to the minus 7 molar, divided over the initial concentration of calcium 2 plus, which is 0.10 molar, multiplied by 100%. And this is just 3.3 10 to the minus 4%. Right, so this tells you that the separation of calcium and barium is extremely good. Okay, notice how the process goes. You have both calcium and barium in solution fully mixed as ions, but then you add sodium fluoride. Because the solubility product of calcium fluoride is much smaller than that of barium fluoride, the first thing that will start precipitating is calcium fluoride. Okay, and what will happen, or that will start to happen once the concentration of fluoride reaches that point, right? But then you can continue to add fluoride, and what that will do is simply bring to the bottom here calcium fluoride selectively. You can continue to add fluoride and fluoride and fluoride, and calcium will continue to fall out of solution selectively. Barium fluoride will not start to precipitate until you hit that concentration of fluoride. All right, so suppose that we continue to add fluoride to the point where we reach just a concentration that is slightly below that. Okay, then we can ask the question, well, how much of the calcium has not precipitated? And that amount is ridiculously small. It's only 3.3 10 to the minus 4% of the initial. So essentially all of the calcium that you had initially has actually precipitated and is now in the bottom, which you can filter out and then separate as simply calcium fluoride. The rest is just a little bit of calcium left over, which is very minor, and then all of the barium. Now you can continue to add fluoride to that, precipitate all of the barium, and then you will have the two salts separated. Calcium fluoride on one hand, barium fluoride on the other hand, and that is how selective precipitation works. All right, so let's wrap this video up. We have seen in this video how can you separate two ions using precipitation or selective precipitation with a counter ion, which produces salts of quite different solubility products.